In this video, we're going to go over the free response review questions for Unit 3. All right, so I'm going to start with this first one, where it's talking about researchers trying to design an experiment to compare two different types of running shoes, shoe A and shoe B. All right, so let's start with question A, which says, what is a statistical advantage of blocking by classification of runner? So I know it's been a little while since we've talked about blocking, but blocking is used to account for a known source of variation in the response to allow for a more precise comparison of the treatments. So in this situation, that response variable would be the running speed. So because the professional runners are likely to have higher running speeds than recreational runners, so the variability in speed across runners should be smaller within each group than it is for the entire group. So by doing this, right, by essentially blocking based on their running ability, professional versus amateur, we are going to give ourselves a better chance of detecting a difference between the shoe types, if there is any. So this will give us a better chance to determine if there is a difference in shoe type. Right? And there may not be, right? That's part of the reason that they're doing the experiment. So again, blocking, remember blocking is they separate the, in this case, the runners, but they separate your experimental units based on some factor, based on some characteristic, and then they run separate experiments within however many blocks that you have, okay? All right, let's do letter B. Why is it important to randomize the type of shoe the runner will wear instead of allowing the runner to just choose which shoe they want to wear? So randomization basically is used to reduce or eliminate the effect of any confounding variables that might be related. In this case, the shoe type associated with our response, where we're looking at the running speed. So if runners were allowed to choose the shoe, so if runners were allowed to choose the shoe, it's possible that runners who choose shoe A might differ in ways from runners who choose shoe B, and those differences might affect their speed. Now, I know the likelihood of that is minimal, but there is a chance that this could end up causing a confounding issue and essentially your experiment results would not be really discernible, or it would not be able to generalize from there. Okay, let's do part C, and then we'll be done. Part C, explain how the design of the experiment will address replication, and what is the benefit of the replication. So the first thing is they're replicating by assigning more than just one runner in each in each classification to wear the shoes. So there are multiple runners in each classification who will wear the shoes. That's how you spell wear. There we go. Sorry about that. Okay. And then in terms of the benefit of it, the idea is, it's kind of hard to explain this in like short terms, but I'll try my best here. If you only use one runner, right, the idea is that runner could have a good day or a bad day, right? If you use 2 runners, 3 runners, 10 runners, 50 runners, in this case, we'll have 25 for shoe A, 25 for shoe B in each classification, I believe. The more runners you have, and looking at a statistic like an average or a median, it's going to help you kind of hone in on what the actual difference would be between these shoes, if there is one. So the idea is that you have less of a chance that you're going to essentially not be able to determine the difference by having more and more runners, right? So if we could get 50, 100, 200, 250, right, again, I would feel even more confident in these actual results from the experiment. So I'll try to explain that real quick. So by having more runners, we can use a statistic that will help us compare the 2 shoes, right? And when I say statistic, right, I'm talking about an average or a median. All right, so that's it for the first one. Hopefully, you'll see here that there's a lot more writing to do in these questions because we haven't really done a whole lot with the calculator. Let's go to number 2. Now, number 2 is talking about a dermatologist that's going to conduct an experiment with essentially a new drug to treat acne. They start off by mentioning that they've got 36 pairs of identical twins, and each person is either going to get the new drug or they're going to get a placebo. They're going to do that treatment for 2 weeks, and then the dermatologist will evaluate, hopefully, the improvement in the severity of their acne. So the first question just says to identify the treatments, the experimental units, and response variable of the experiment. So this hopefully should be like the goal here is this should be like gimme points, right? They're trying to help you out with this. So the treatments are the new drug and the placebo. Don't forget to mention, if they do say there's a placebo, that technically is a treatment. Even though the placebo doesn't include any medicine, it's still technically a treatment. Okay? The experimental units, we don't usually say experimental units for people, right? But in this case, the experimental units are the 72 people who receive the new drug or placebo. And then finally, the response variable. So what are we like kind of evaluating? What are we writing down? And it mentions that kind of the end of that paragraph, after 2 weeks, the dermatologist will evaluate the improvement in acne severity. So the response variable is the improvement in acne severity. All right, so again, that's kind of just a reminder about the vocab that goes along with this idea of experiments. Okay, part B. It says, Each twin in the experiment has a severity of acne similar to that of the other twin. However, the severity of acne differs from one twin pair to another. The dermatologist experiment, there we want to describe a statistical advantage of using a matched pairs design where twins are paired, then rather than using just a completely randomized design, so where we don't really take into account at all the fact that these are twins. All right. So what I would say here is kind of the main statistical advantage here is this allows us to, when we compare the improvement in the acne severity, if we're only comparing, one pair of twins at a time, like to each other, then we can say with more confidence that the improvement or lack thereof would be due to the fact that they're taking this new drug, right? There are other things that go into the fact that acne occurs in your body, and I assume they're talking about their face, like diet, genetics, things like that, stress level. So again, by using the twins, right, the matched pairs idea is we can hopefully kind of account for that variation and hone in on just the difference that we care about, which is the difference between the placebo and the new drug. So, kind of to sum up here, so because the pairs are similar in acne severity, pairing allows for the variation in improvement scores due to treatment, unlike in a completely randomized design, right? Because if we just do a completely randomized design, we're going to be comparing essentially 36 people that took the placebo, 36 people that took the new drug, and there could be identical twins in one group or the other. Could be twins in the same group. So ultimately, we're not going to be able to kind of say that our difference is based on just the treatment when there are other factors that go into the idea of having acne. All right, let's do C. For the dermatologist's experiment, describe how the treatments can be randomly assigned to people using a matched pairs design in which the twins are paired. So the way I'm going to do this is for each pair of twins, assign one to be twin A and the other twin B. Flip a coin. If it's heads, the twin A is assigned the new drug. That's not how you spell drug. Drog. If it's tails, then twin B is assigned the new drug.